Welcome to lecture 31. In this lecture, I want to talk about black holes. So in old world maps, you sort of have sometimes the areas of the world which are not well known, and these appear either in white, or there are some certain regions on these old world maps where early cartographers made some specific uh, signs that these were unexplored areas. In particular, if you look very closely, you find signs that sort of look like these. And it says Hic sunt dracones, which basically translates to here be dragons. And that was basically the old timers' way of expressing that these are unknown areas and we don't really know what's going on there. There can be anything happening. There can be dragons, there can be monsters. So what we want to do today is we want to talk about monsters in the universe that actually exist. We want to talk about black holes. Um, we have to sort of get out of our local home world. We have to sort of go away from our solar system because in our solar system, everything is explored. There are no black holes there. So we have to venture out into the not so well mapped regions of the universe. And if we look out of our solar system, then there are some neighboring solar systems. In particular, there's Alpha Centauri, which is the next star to our sun. And then we have some other systems that are in the local clouds. So in the radius of on the order of 10 light years, we sort of have looked at solar systems and we have not found any black holes there. So we have to venture further than that, venture further outside of our local cloud, basically. If we do that, then we start to explore the regions that are in our vicinity, our neighborhood in the Milky Way. That's our home galaxy. Um, this is a artist's depiction of the Milky Way. We are located roughly here, and there are literally billions of stars in the Milky Way. We are at sort of somewhere outside here. And indeed, if we go to a scale on the order of the Milky Way, it turns out that we do have black holes on those length scales because we believe, we actually have very good evidence that there is a black hole in the center of our galaxy sitting right there. Next, I want to talk a little bit about how black holes actually form. It all starts with stars, such as our sun. Our sun is a main sequence star. It is about halfway through its lifetimes of about 10 billion years. And stars have the property that they support their own gravitational weight through the pressure that they sort of get from solar fusion. So basically what they do is they get energy by fusing together light nuclei, such as helium and deuterium, into heavier nuclei. That creates energy, and the energy creates thermal pressure that allows the sun to escape its own gravitational pull, which would like it to sort of compress it down. But because it's so hot, there's so much pressure, that pressure sort of keeps the balance, and the sun more or less retains its own shape. If we want to sort of go to the far future, we can sort of see what the evolution of stars generally looks like. So I said that our sun is mostly fusing light elements such as hydrogen and helium. It fuses those together to make heavier elements such as carbon, neon, and so on and so forth. Now, the amount of helium in our sun is extremely high, but it's limited. So at some point, stars essentially exhaust their amount of helium. In particular, there is a length scale or time scale that we can associate with a typical star um, essentially exhausting all its hydrogen fuel. So basically, if we look at the main fusion process, which is hydrogen to helium, the typical time scale over which that fuel is spent for a star is on the order of 1 billion years or 1 gigayear. Once the star has exhausted all its helium, it basically sort of starts to sort of burn whatever is left. In particular, it starts to burn helium to carbon, um, but you get less energy out of that reaction, and the star can maintain its shape for another 100 million years or 100 mega years by doing that fusion process. But at some point, also the helium is exhausted. So the star resorts to the next step, which is burning carbon to neon. Um, and again, the sort of energy that you get out of that is limited. So the carbon to neon process supports the star for another uh, time span on the order of 1,000 years. Once that is done, it starts to burn neon to oxygen. It only lasts 1 year. Once that is done, oxygen to silicon only lasts 6 months. And once you start to burn silicon to iron, that supports the star only for another day. Now, once the star is done burning silicon to iron is the most stable of nuclei, which means that you can't get any more energy out of burning iron to even heavier nuclei. This is where the buck stops. Once everything is burned into iron or heavier elements, the star has run out of fuel, and there's nothing to support its own gravitational pressure. So what happens then is that the star, at some point in its last day, runs out of fuel and it collapses, and there's a shock wave that comes out that is essentially the remnant of the star that's blowing itself apart. This shock wave sort of flows outwards, and it creates this flash of light that basically sort of is visible very, very far away, and is so energetic that this single star basically, for a brief moment of time, is able to outshine a whole galaxy. So this was a simulation. That was a simulation that is created by people doing numerical relativity. In particular, that is the group at ESA. And however, these pictures that you get from the simulations are very close to what you can see in actual sort of systems that have undergone a supernova. So what I'm showing here is a particular observation of a star system that has gone supernova about 1,000 years ago. It looks like this. So this is an actual image. Here's another one. So you can clearly sort of see the shockwave still sort of exploding outwards. Here's a third one. And these are sort of real observations. And we sort of believe that we understand that part of the evolution of a star, so the last moment and after star's death, from our simulations of relativity. Now, what happens after the star has gone nova depends on the star's mass. If you have a star that is fairly light, so small star, then its evolution will be that it once it sort of runs out of fuel, it will sort of produce a red giant. It will explode and produce these planetary nebulae, such as the ones that we have seen, and it will leave in its center a compact object, which is known as a white dwarf. A white dwarf is a dead star that no longer does fusion, but it's still hot, so you can still see the emission of light from its surface if you have a very, very powerful telescope, for instance. For heavier stars, these become so-called red supergiants, and they really sort of undergo these supernova explosions, such as the Crab Nebula here, that was actually sort of observed by people back in around 1000 AD, because that star, for a very brief moment of time, outshone the whole galaxy, and it was clearly visible in the night sky. So the remnant of that supernova, then there are two possibilities. One of them is to create an even more compact object than a white dwarf, which is known as a neutron star. Again, a neutron star is a dead star. These neutron stars are extremely compact. They pack the whole mass of a star, for instance, our sun, into a radius of about 10 kilometers. It's extremely dense, but it still is sort of, some people liken neutron stars to basically an atomic nucleus with a radius of 10 kilometers. That's basically one good way of imagining what a neutron star is. However, if the star is even more massive than uh, these progenitor stars that make neutron stars, then the gravitational pull from the star's own weight cannot be countered by the neutron pressure. And if that happens, the star continues to contract, and what we find at the very end is indeed something that we call a black hole. What is a black hole? Basically, it is a dead star that has been so heavy that its own gravitational weight cannot be supported by either the electron pressure in white dwarfs or the neutron pressure in neutron stars. It's so dense that all its mass gets uh, pulled in, and it gets pulled in to such an extent that at some point all the mass is within the Schwarzschild radius of the star. So what that means is that we have a Schwarzschild radius here, where we have our outside geometry, where there's essentially empty spacetime, and all of the masses inside the event horizon, the Schwarzschild horizon, um, with a singularity at the very center. Now, why is it called a black hole? Well, it's a black hole because a photon that is emitted very close to the Schwarzschild radius and sort of is traveling outward, even though it's moving at the speed of light, it has to climb out of the gravitational well, and the energy that is needed to climb out of the gravitational well is so big that photons essentially don't make it out, or alternatively, they make it out, but their energy is redshifted. Sorry, their frequency is redshifted, such that even though sort of they make it out to infinity, they appear just as black photons. So they don't have any color, and that's why we call these objects black holes. Now, there are a number of people that have had an outside impact in studying black holes, and I want to mention just a few of them without trying to be complete here. Obviously, one of the main people who has contributed to studying black holes is Albert Einstein, who wrote down the theory of general relativity in 1915. And basically, the theory of general relativity is needed in order to make quantitative statements about black holes. It predicts black holes, and it's sort of necessary, the mathematical structures necessary to really sort of make concrete studies of black holes possible. The person who first found solutions to these Einstein field equations was Karl Schwarzschild. And he wrote down the solution that we sort of nowadays study to nowadays use to study the simplest version of black holes, so-called non-rotating uncharged black holes, Schwarzschild black holes. Another person who has had a tremendous impact on black holes is Roger Penrose. Roger basically in 1965 wrote an article that essentially said that black hole solutions are not just a mathematical curiosity, which is what people sometimes have thought up to this point, but they are actually real. And Roger's contribution to this field has been awarded by the Nobel Prize in Physics last year in 2020. Another person who has had a strong influence on black hole physics was John Wheeler. Indeed, he coined the term black hole back in 1967, except that that's not really true. It turns out that the term black hole was already used in an article by a journalist called Anne Ewing in 1964, so 3 years earlier than John Wheeler. And it so happens that Anne Ewing also didn't really coin the term black hole, because she said she had the term black hole in a conference that she attended a few years earlier. So at the end of the day, there's somebody else who coined the term black hole back in 61 or something like this, but we don't know who that person is, but clearly it was a very good invention. Another person that has contributed a lot to the study of black holes is Stephen Hawking. So Stephen's main contribution in that regard, for instance, was to show that black holes, even though they are sort of called black holes, are not actually black. So he did this in 1974 in a very far-sighted study, and this phenomenon that black holes are not really black is sort of talked about in the context of so-called Hawking radiation, and that basically sort of means that if you uh, merge the theory of general relativity together with quantum physics, then you find that it's not possible for black holes to be really black. They have a small amount of radiation if they are large, and that radiation really was invented by Stephen. I had dinner with Stephen once in the Old Kitchen in Cambridge University in the UK. Um, well, I should maybe mention that beside me, there were about 30 other people having dinner with Stephen because this was a conference dinner, but it sounds a whole lot better if you say that you had dinner with Stephen Hawking than if you say that you had dinner in the same room as Stephen Hawking once. Regardless of the fact, I do distinctively remember that Stephen sort of made some very good contributions to the conference. I also remember that once in a while his Skype would go off and would basically blast the Skype call in the middle of the conference, and then somebody had to come and stop it. So this made for enlightening sort of pauses in the talks from time to time. Two other people that deserve a lot of credit in the field of black hole physics are two observers, Andra Getz and Reinhard Genzel, who started observing black holes not from a theoretical point of view, but using the ESO CAC telescope starting in 1996. They were making observations of the black hole in Sagittarius A star, which is our Milky Way black hole. And for their work, they were also awarded the Nobel Prize in Physics in 2020, joined with Roger Penrose. Furthermore, we have had the luck, if you want so, to have another big collaboration that has contributed to the field of black hole physics fairly recently. That is the so-called Ligo Collaboration. Ligo was able to first measure gravitational waves from the collision of black holes a few years earlier in 2016 using their interferometer. So this is a picture of this interferometer here. You need some very long baselines on the order of a few kilometers, and these laser interferometers are extremely precise, which is what you need in order to measure these extremely weak gravitational waves from far, far, far away. But basically through advances in technology and R&D, this was finally possible in 2016, and they were awarded the Nobel Prize in 2017 for their discovery of gravitational waves. Finally, let me mention that there has been another very important contribution to this field, which is coming from the so-called Event Horizon Telescope, or EHT. This collaboration was able to take a picture of a black hole. So here it is. This is the picture of a black hole. And what you should be able to see is that there is a ring around this black hole from matter that's basically sucked into the black hole. It's accelerated, it's rotating around the black hole. And because these are charged particles and they're colliding, these charges radiate. So this is the radiation that we see. But in the middle, there is this shadow lurking here. And that really sort of is basically the, if you want to, the event horizon of the black hole that is or was really sort of photographed in this manner by using their essentially worldwide collaboration of telescopes back in 2019. So it's a very exciting time to study black holes. There's a lot of observational data coming in. So there is hardly any field in, if you want to, physics or astronomy today that has not benefited from these new observations. And we will come back to many of these features as we continue our course on general relativity.